Okay, for people joining this live stream, we are going to try and explore a little bit more some of the pandemic data that we've been accumulating and see what we can learn. And today, I'm not going to be driving for once. Christopher is going to be driving. He types and thinks a bit faster than I do. So let's start there. I thought the thing we would do first is try to make some visualizations. We started on a live stream last week, but I wanted to see how much further we could go about comparisons between what's been happening with the pandemic in different countries. So maybe we could start off.
Sure.
I think we were looking a little bit at growth rates and things.
Sure. Yeah. Well, okay. I mean, so there's this resource object, which I believe has the number of cases and deaths and so on by, oh gosh, it's kind of large, but by country and by administrative division and so on. So let me.
Right.
Oh
so let's first of all let's aggregate, complete countries.
Yeah.
Then,
so we should probably say, well, okay. So we'll say that'll be the basic thing, and then we want to group them by country because I think that's one of the values. Or keys. Right, so there's country. So we'll group by country, and then and we want the total of the confirmed cases.
Okay.
And that should, yeah, there we go.
Okay.
One there instead of total. Confirmed cases are cumulative.
Right. But the thing is, so if we look at the point is that if we look at
yeah, got it. Yep.
Yeah, so
totaling over states and provinces.
Right. And now the only hope is I'm pretty sure that when it lists administrative divisions, it also doesn't list the full country. Right?
It does.
We should wait. So it does. It'll list administrative divisions, and then it will also list the full country.
Yeah, I think so.
Yes, it does.
Oh, well, then the thing is, though, is that wait. But then the thing is, if I say of all,
it doesn't list it never double counts, right? Any given thing is just on a single line.
Correct. I don't think you will find a separate United States or a separate China row.
Check. Okay. Oh yeah, that's what I was guessing. Right. Yeah. So we've got. Right. Yeah, I'm pretty sure that's right. Like if we just say, let's just say selective hash.
We've got 54 rows. That's a little bit odd.
Wait, why are there multiple ones that have this? Oh, those are probably the cruise ship.
How can there be three? Are there really 3 cruise ships? Let's find out.
Let's.
And there's also some of the territories that may be showing up in some weird way.
Yeah, so we've got missing cruise ship, missing Wuhan evacuee. Okay, so I mean,
this is the joys of data curation. That you think you're getting states, but in fact you have cruise ships.
Yeah.
Well, I like this missing. I mean, because missing has this the reason for being missing. It says from a cruise ship.
Right.
The best though is I think that there's a country. I think that one of the countries here, if we look at if we look at the keys here, I'll say normal. One of the countries is called not a country cruise ship.
Okay, right.
Yeah.
So that was a cruise ship that isn't part of. That isn't a U.S. I see. Those ones were repatriated people who were U.S. people who were on the cruise ship, whereas the entry here is the remaining people on the cruise ship, presumably.
I guess so, or something like that.
May have been slightly wrongly counted. Actually, a question here is which countries are not in this list? We just do a compliment.
I mean, we can just say, yeah.
Countries maybe.
See.
And then we just want to compliment, presumably.
Okay.
So why don't you sort by population
Yeah.
or reverse sort by, or whatever? Why is that taking it? Oh, I see it. It was
Well, there's a more
efficient.
efficient way to do this, which is you say now it's whoops.
You're going to want the country and the population.
Well, this is I need to do entity association here.
Yeah.
But now it's sort of gotten. I'm gonna abort. Okay, so now we'll just say here.
You need to reevaluate raw.
Yeah. Okay, there we go. Antarctica. Okay, well, we've got.
So Myanmar is the most populous of those.
Although I thought that Myanmar did have some cases, but I could be wrong. I'm not sure, but yeah.
Well, the good news is it's hard to have cases when there aren't any humans there.
No, we don't need this entity value anymore, but.
Oh, it's interesting. Huh. Well, fair enough. Okay.
Okay.
Hey, don't forget to save this notebook.
Yeah.
We're generating all kinds of interesting stuff. Okay. All right. Let's go back and try and look at the actual growth rates.
Sure.
So we had.
Whoops! I deleted this. The thing that we want is this. Yes. So
right.
So we have the country time series,
right,
which will be this. And so this should be the map from association from countries to the time series of the confirmed cases. By the way, I assume that the confirmed cases, it just goes up. It doesn't go down, right? Like
that is correct. It's cumulative.
Okay.
Actually, Sandra on the live stream is saying it'd be interesting to look at number of cases versus population. We should do that. That would be easy to do. Let's
sure. So we'll just say country TS of. Is there a actually? I wonder for time series if there's a last value. I mean,
just as an
aside,
values. There is one
value.
country or administrative division where the confirmed cases goes up and goes down, but it's a very small number overall, like only 10 cases.
Oh, because of recalibration or something?
I don't know. I didn't look into it, but I noticed it on Sunday.
It could also be because of movement. Like because I was wondering about this as well with the cruise ships, right? When it's reporting, for example, the infected populations like the US, right? So it has those curves for the cruise ships, but most of the people have been taking off the cruise ships.
Yeah, that's right.
And so you'd expect the number should go down if you want the total to be correct.
Okay, so anyway, let's look at.
Yeah, so we'll just say. Let me see. So we want to look at. Well, we'll do it like this. We'll do. Okay, for now, let's just say we can do that. But then, if we want to correlate it with population, then we want to. Is there a fancy way to do this? And we can just say key value map, but that seems well. Okay, we'll try key value map.
Don't forget, it's not. I have to get rid of the /add.
Yeah. But the thing is, this will be less
that's
efficient.
not efficient because it's you want to do it for the keys first.
So we'll just do it like this. We'll do.
And you might want a tooltip for the country.
Sure. What do we want? We want this on the x-axis, and we'll say.
When you tooltip
okay,
the
this is kind of the. Yeah, I mean we can do this. This is not the prettiest code. Okay. We might want to plot we might want to make the population on a log scale, because otherwise.
Yeah, but that's interesting already. Okay, so what that's showing is
Perhaps even on a log scale.
Yeah, let's try. Let's start with log, and then we'll add another log. We're still not getting China, for instance. Let's set the plot range to all.
Yeah.
Okay.
Wow. Okay. Right. So keep that plot, and then let's also make the plot with plot ranger automatic. Okay.
Oh wait, but so we want. Okay, no, but for this one we want log, or we want log linear at least. Okay. Let's actually start with the list log linear, and then we'll go to log. Okay. So this is showing the population is on a log scale, but the number of cases is not. Arguably, you want to look at the
because capita, right, but in an exponential growth situation, the number of cases would be. Well, I don't actually understand why that would be relevant. I mean, the log seems more relevant here.
Well, but arguably, we should also look at the per capita cases.
But let's scroll down a bit. Let's look at this log for a second.
Yeah.
What's that one trailing behind China?
The US.
Great.
So you get, because here's the population. There's China, India, US, Indonesia, etc.
Presumably that's Italy by Spain.
Yeah, this is Italy.
Sandra is suggesting an animation of this over time, which we could do.
That is, that actually wouldn't be too bad. Let me see. So we just want to basically say, so here's how we'll do it. So instead of that, we'll just say.
I don't know if that's going to work, because they'll be different length time series, won't they?
No, they're all the same length. Oh, why is some of them missing though? Well,
maybe that's the most recent value.
We'll try it. So we'll say basically, we already have that. What should we call this?
Sequence or something, or animation.
Okay. And then we want to say all comma. Does this work? No, that's it. Only query can do that. We'll try this. We'll say manipulate list log plot of. We'll probably want to fix the plot range. Animation part. So here's another question. So if I have this, I say part all comma 1 comma. I don't think I can do this. No, okay, we'll use query instead. So the point is that you need to drill in and get a specific element of this. But we can do all comma 1 comma.
You can't be doing nested queries.
That's the point of queries, that you can do nested queries. So this is the n. This is the n, which determines the time.
Okay.
So okay. It's only a bit cryptic.
Why is that red?
Oh, it wants a dynamic module. And we'll just assume they're all the same length. We'll make this n. We're going to want to fix the plot range.
Wow.
It's a bit slow.
It's a bit slow. It could probably speed it up by pre-computing
the plots. I mean, I could turn this into a table and then make it that might get a bit big though, I'm not sure. nested queries are this is kind of it's not really, this is, I think, kind of the point of queries, is that you can have nested queries. Because it means that you can, basically, when you have a query inside of another query, it's the same as if you had parentheses, because you're basically saying that I want that's why query is only as an operator form.
All right, what's this doing here? So,
I think this is,
and then,
I'm
all
not
right, once
super
we have
hopeful
this,
about this, but yeah, okay.
well, maybe we should just do the manipulate, where we could at least see some values, because I think it's going to be interesting to see. You want to get rid of the table.
Yeah.
What is that? Oh.
No
Okay.
idea.
Well, I know what it is. It's the control for a manipulate, but it's not relevant for this. Okay. So this was early on, and now let's go like to the middle or something. And clearly.
Okay.
Oh yeah, that's a good point. Somebody's suggesting using parallel table. I don't think you're not running on a particularly crunchy computer here, but
Yeah, although I could run it with like 10 kernels. I think the computer actually has 6 cores, but thinks it has 12. So, but okay.
Okay, well that's interesting. All right, we can separately let's generate this separately. We can generate this offline, or if you save this, I could run it. I have 100 cores here. So
okay, well, how about I can whoops. I can try and share this notebook with you somehow.
Put it in the cloud.
Yeah. Or let me see. Okay.
Oh, there we go. Okay, great.
Yeah.
All right. So let's go back to what we were trying to do, which was we're trying to look at growth rates and things.
Yes. So let me see. So we already had that.
We had, first of all, we had the aggregated numbers of cases by country, right? The time series.
Right.
So let's go back to those time series and let's start looking at some growth rates.
Yeah. So we should arguably we should say we should get all the values for these, because I'm pretty sure the length of all of these is the same. Oh, I don't want length like that. I want a hash of what is it for a time series? No. So for a time series, then my point is I'm pretty sure these time series all have the same exact structure, and they all have the same number of data points and everything. So if I say how
about value dimensions?
Value dimensions, is that what it's? Okay,
it was in the table there, so
I'll try it. They all have 62.
Yep. No, that seems to.
Oh, it's value dimensions is if it's 2-dimensional. If
the valued payload is not 1-dimensional.
Gotcha. Yeah. Okay.
But the point being that the fact these are in a time series is kind of for many purposes we don't.
I see. You're suggesting we just want the values.
Yeah. So
starting off from.
Yeah.
Okay.
What this is just right. The time series as a vector. Again, I don't know why. We might want to get rid of some missings, but I think it's fine for now.
Okay.
So
now we want to look at growth rates.
Yeah. So now let's try.
I think the obvious growth rate is just ratios, day-to-day ratios. But we then
sure.
why
don't we first start with just the log plot, and then we'll go from there. So if I just say list line plot of this. So this is the most basic thing. Okay, this is a mess. Mm-hmm. So one of the things we can do is we can line up when they start going up, right? So we can line up all of them so that they're in the same place. So we could just say, well, for each of these, for each of these, we can just trim off all the zeros at the beginning, maybe up until it's like 100 or something like that.
Right.
Well, because it's just strictly increasing, we can actually just say this, or we can even be fancier.
Okay.
Right.
So now for those, if we plot that, we should get.
Whoops.
That's that silly thing that you need to do a delete cases for the list line plot. Since Brett is here, we can point out that you shouldn't have to do that.
Oh, it's because of these.
Right, yeah.
Yeah, I think it's because if it's a list of if it's a list of lists, then there's maybe some ambiguity, but in this case there isn't because it's an association. Okay, but let's.
Yeah, I think that one we had actually noticed late in the 12.1 cycle, and it was like, we're not going to try to tackle that now.
Can we instead of using?
Yeah, we'll say.
I'm with a joined. I don't think there is one of those.
I was checking.
Okay, so that's the logarithmic growth rates.
Yeah, so I mean, at some level, the thing that's interesting is the slope.
Right.
And the slope over time.
I think we should use ratios. Which is,
yeah. We can use ratios, or we can use.
Leave that plot. Don't delete that plot.
Well, so
what's
okay,
the second country in blue that leveled out? Is that
this one?
Yeah.
Why don't we label these more properly? So we've got that's China. That's not a country cruise ship. Not surprising it leveled out. Right. Okay, but we'll see what all these are in a minute probably. So let's okay. So now there's a question though. Sorry, let's start by doing ratios. But I predicted there's going to be a problem. So we have that, and then we're going to say ratios. Why does it do it exactly if I?
Yeah, why does it?
Let me just look at
that n didn't nest the way you thought it nested.
Ah, yes. So actually, you know what? I'll just put the n here. It doesn't really matter where it is. I'll fix it up here because it's kind of weird what's going on there. Okay, so then we'll say ratios, and then we'll say.
So that's the day to day. That's the ratio of the number of cases from one day to the next. That's the daily.
Right. So that's the This is saying over time. Let's fix this. Starting with the over time, what is the change in the number of cases
day to day?
Yeah, as a fraction.
Right.
All right, so let's do a more intelligent plot range though. So the x-axis, let's say, is all for now, and then the y-axis we should do 1, 2, because they're basically strictly increasing. Let's do 1 to like
2.
We'll start with 1 to all.
Okay, and then I would do only. I mean, why don't we just do the 30-day?
Yeah.
Okay, so that's showing the daily ratios, which are clearly kind of a mess.
Well, okay, one thing is that if there's a country that has 10 cases and the number of cases changed by a factor of 2.
Well, but remember, we started at greater than 100 here.
Well, okay.
We only started this picture at 100 cases. So there shouldn't be that much fluctuation. So I think we should be using I think the next thing to try is something like this mean filter idea, where we're looking at where we're taking not just the daily, but some kind of thing where the sequence is replaced by the mean of the where each value is replaced by the mean of a sequence of neighboring values. So that would
right. Although there's a question though of, do you want to do the averaging before you take the ratios or after?
I say after.
And the last option is you take the log, then you take the means, then you take the ratios of that.
Well, differences of the logs.
Yeah,
because the ratios will give you.
No, right.
But I think let's look at all the different cases. Okay, so the first thing to do, I think, is let's take this and let's take mean filter on those ratios and see what that does.
So we'll say.
I should leave that plot. Copy it down so we have another one. I think you want to do mean filter on the ratios. Oh, I see. Mean filter of that. So, okay, so that'll be. Is that 3 days on either side?
I assume so. Range R neighborhood, yeah.
Yeah, so that means it's n days on either
2R
side. That's
plus
a lot of.
Yeah.
Okay, so why don't we make it 2 instead of 3? And also, I think we're going to end up. Oh, it surprises me that we're not ending up with countries that have too few values. Okay, so what is the
saying delete cases on the outside?
Well, I mean, there's one that's in a turquoise that's 2 data points or something at 1.5.
Right.
Yeah.
But
yeah. Okay. And you see there's some things you can see here. I mean, you can see there's sort of a downward curve,
which is good if that's really true. But let's try to understand. I mean, so just to recall what this actually is. So this is the smoothed daily ratios as a function of time. So maybe we could try and let's try and prune this picture a bit so that we see just a few countries, because it's kind of a mess right now. And I suspect that in those early days, that when the numbers are still quite small, these ratios are not going to be as meaningful. So I mean, what we could do here in this picture is we could select only things where the absolute value before we take ratios is bigger than something. So in other words, only countries that have, let's say, 1,000 cases or something.
So we're selecting the countries that. So we're trimming off the first until they have 100 cases, but we're also only looking at countries that eventually have.
Yeah, where the last of the thing, well, not necessarily. Yeah, where the last is greater than 1,000.
So we'll say select of this, and we'll say we can say I'll just say max because I think it's more clear. So here are only countries that eventually have more than 1,000 cases.
Wow, why don't you make that 3,000 cases? Okay, let's take a look at that for a second. All right, let's see what's going on here. So can we label this in a way where we can actually label it? Because I can't match these colors up quickly.
Well, we can try
call outs or something.
Yeah, call out. That's not too bad.
Okay, let's take a look at that picture for a second. Okay, so what that's showing is, for example, that the ratios, for example, for Italy are progressively going down. That's good. I mean, of course, it's compounded by testing artifacts and things like that. Let's see, where is where's Korea on this list? Does it not have? Did it never get to 10,000 cases? Well, let's keep that picture, and let's do the thing for 5,000 as well.
Yeah. Why does it say countries?
Because it's got both Korea.
Oh yeah. Yeah.
Wow.
Okay, so we'll try 5,000. Right now the call outs are not quite.
Hey Brett, can we make those call outs better somehow?
I think you might be on mute.
Good guess, Christopher.
Is that the best we can do, or can we do some? So what's the best way to do it?
I'm trying to think. I mean, what you were doing originally should have been good. I'm wondering though why we were getting. Oh, we're getting crosses because they don't all go to the same, all the way out to the right edge. Okay.
Yeah.
By the way, this picture will be a little bit easier. Why don't you just say plot style arrow thick or something, or plot style arrow thickness point?
Is there a plot
01.
theme? I don't know.
Oh, there might be a plot theme.
Try plot theme goes to dashed. There's some dashed lines. Sorry.
Lines. Okay.
I don't know if that helps.
Actually, that helps a little bit because you can distinguish some of these lines that kind of cross each other.
Right,
well, I mean, in this case, I mean, I wonder if the legend will.
Yeah. Okay. So try a legend.
We'll just do it here because.
Okay. I'll try making it bigger. I would try having plot style arrow thick or something. Or is that going to mess this up?
I mean, it'll look a little bit weird, but you'll still see the dashing.
Really? Okay.
Does that make it thicker? Oh, I think I might need to put it after the plot theme.
The order doesn't matter.
Well, you might need to say thickness 0.01 or something.
Yeah, absolute thickness of, thickness of.
Okay, there we go.
That's a bit much.
This is hard it's hard to read this.
Well, I mean, so, okay, why don't we try, okay, here's another thing to try, is just take the average of all these curves.
Okay, but leave that picture, because I think that picture is interesting in its own right.
That picture will be left there. But now let's try this. So we'll start with just the greater than 5,000, and we'll say values, and we'll say, well, I guess we kind of want to, let's see, what's the nice.
You're trying to make them all the same length, but what you're trying to get the ones that are.
What we want to do is we want to take the average of all the ones that appear here, the average of all the ones that appear here, and then the average of all the ones that appear here at each step.
Right. I just wrote something actually called ragged mean around, which might be in the function repository. Just try saying resource function of ragged mean around.
I mean, it seems like it's exactly the thing. Is this it?
It might be it. Just try that.
Let's whoops.
I don't think it's yet. Just try it. I think it should just
version
work.
2. Okay, so we'll, yeah. I'll make copy the fancy.
Okay.
Okay, that looks like it might be it.
Oh, that's quite interesting. That is quite interesting. Now,
so note the number of things that we're averaging goes down quickly. So and that the ranges are different here. So 30 is here. And after that, it's basically just China, I think.
Right, but that's interesting. I mean, so that the fact that why don't we do the most obvious thing? Let's just get the worldwide data and let's do this for the world. Oh, I see. The worldwide data doesn't work because you have to initialize everything at a certain point.
Right, so we can get rid of the 5,000 here maybe, and then we'll get. So this is for all countries, not just the ones that have eventually had a lot of cases.
That is an interesting plot. That really is an interesting plot, but maybe it's dominated by China to too great an extent.
Well, no, I mean, because China has the same is averaged in the same way.
Oh, I see. So China only counts for 1 in this averaging.
Yeah. Correct? It's not weighted by population or anything.
That's really interesting. That plot. That's a very encouraging plot, right? Because that's saying that basically the successive ratios essentially go down from a maximum. Hey, Bob, in the world of R0s in epidemiology, what can you read from this? Is this effectively giving us a version of what R0 is?
I'm not sure. I'm still trying to digest exactly what this is showing. I'm surprised that it's declining over all time like this. Well, I would have expected the ratios to be going up initially and then come down.
Well, we're cutting out. a little bit. So I mean, we're only starting.
Why don't you
go, wait. No, I see what you're saying. Yeah. So the ratios start out fairly high, which means it's a steep slope, and then it levels off.
Right. That's what this is saying.
Yeah. Yeah.
Okay. So here, make another picture, Christopher. Copy that, and then let's change that greater than 100 just to see what happens.
Yeah.
Change it to greater than 50.
What happens if I make it greater than 0? Okay, I mean, that's kind of, I mean, the point is that the ratios are pretty meaningless if you don't have a lot of people, because it's just
right. And this is weighting. This is weighting every country. You know, this is like, you know, slots at the UN or something. It's every country weighted with a single slot, not weighted by population or anything like that.
Yeah.
That is a very interesting plot. That's so.
It's very linear.
It's very linear. What the heck is that? So in like the SIR model or any of these other models, can we explain why there's linearity here? It's strangely linear.
So what happens if we do the ratios on the cumulative across all countries at the same time? You know, which would take the population into.
Yeah, but you see, that's not going to work because each country was seeded at a different time.
Right.
So what this is showing is, given that you were seeded, I mean, let's change. What did you change? Oh, that was.
So I got rid of the mean around. I mean, I guess
filter. The mean filter. So that's showing the daily. Okay, so hold on. That is also quite interesting. I mean, so that's the daily ratios. That's in a sense we're reducing the amount of data processing that's going on here. This is just each country counts for 1 unit. What did you do?
I love that periodicity in there, but it's like every 4 days.
Yeah, I don't know what that is. That's something weird. Okay.
Well, so part of this is just that the error bars are tall.
Could you go copy down this thing and then say forget the max greater than 5,000. See what happens if we just go to
yeah, that's right. So oops. Oh yeah. Yeah.
Okay, so
we have
that's
we have 4 analog plots. We've got this one is associated with this one, but without the mean filter, and then this one is associated with this one.
Right. But so that one is okay. So let's just understand with minimum data processing. That one is every country is considered to be seeded when it has 100 cases, and then this is simply asking the daily ratios for those 100 cases. I think that's an interesting plot.
Yeah, again, it's surprisingly linear.
It's really surprising. Why would it?
And so this number here is basically the R, right? I mean, in principle, this number here is the R. If it was just perfect exponential growth.
Yes, right, exactly.
Average R over time after you've hit 100 cases.
Right. Let's see. What can we do for this plot? So, what this plot is saying is that previous plot that we have. Okay, a question on the live stream from Brian. Does this growth rate mean it's leveling off in a logistic curve? I don't think so, but let's think about that. I mean, so what we have is an exponential. This is ratios, the successive ratios are going down linearly.
I have the feeling that we could observe that with a Gaussian, like the beginning of the Gaussian.
Okay.
But I'm not sure. Because it's kind of a, if it was exponential a coefficient time x, we would see something straight. So it's kind of exponential a function time x, and this function is linear, which gives an exponential of a second order polynomial.
So instead of it being r to the t, it's mt to the t. Or this is the slope of,
I mean, I said like instead of exponential x,
exponential of t.
I mean, instead of exponential of t, it's more exponential of t times a linear function of t. Time f of t.
So t times a linear function, or this is a minus bt.
Since it's a line.
Why are we doing this? Let's just take that data and let's try and fit it. Let's find a let's just take the central data from that last list line plot.
This one.
Yeah.
This is the simplest one. Okay, now I'm gonna propose we chop it off at 30 though, because this is like there's only like one country that goes that far. Actually, out of curiosity, I'm just gonna try saying yeah, there are like 3 countries that are above 30. So we'll just chop it off at 30.
Okay.
Yeah. Okay. So.
Wait a minute. In terms of understanding this data, it isn't the case that the reason that the early values are high is somehow because more countries are contributing. No, I don't think so. It's just that, I mean, there were countries there with only one data point in this picture.
Yeah. I mean, this is right. I mean, this is looking at, you can see for individual countries, if you look at South Korea individually starts high and it goes down.
Mm-hmm.
Right. And what's this? This is Iran. Well, Iran principle starts high and goes down, and they all start high and go down. So I think it's not because there are more countries.
Yeah. Okay.
But okay. Let's see. So if we take this and we say, does up to work with part?
What is that? That's really weird.
Part's tearing apart the around or something.
It's on the wrong side of the mean around. There, now it's right. Okay, so now if we say, just to check, so this should go up to 30. There we go. So now we'll say.
Now you want the central values of that.
Central values, because of
because yeah, it's mean around, and I don't think the fits will work yet with mean around.
Are you sure? You can try.
I can try it. Yeah.
We'll try. What is
Good luck. I don't think that's going to work. Right. Try just an ordinary fit. That might work.
Fit or find fit. We'll try.
I would recommend fit, the simplest stuff. And then I would just say, well, this is going to fit a linear function. MBX.
Oops.
Number of coordinates is not equal to the number of
Wait. I'm not doing this right. Data. Oh yeah, I'm doing find fit inputs.
Yes.
It should just be
1x. Okay.
It does work with around.
And why is it saying x minus? No, that looks completely wrong. That means
I think that's x times negative.
That's an interesting bug. Somebody write that down. That's a bug. That's a display bug.
Yeah.
It's an interesting display bug. Okay, so that's giving us all right, that's a fit to that function. I think that's a really interesting function, but I want to understand that better. I mean, it's very strange that really messy data, when aggregated, turns into something as simple looking as this.
Well, you can put it back into the, we can
let's superimpose it. That's a good thing to start off with. I agree. Let's superimpose it on that original data.
Let me first try. There's another resource function. I think it's called regression plot. No, okay. So I think there is a thing for that. But let's try it with let's try it like this. We'll say.
Oh, I didn't mean the fit. I just meant that aggregated thing. I just meant the %94, the aggregated thing. Just show it along with that other data, just to see what it looks like.
Which other data?
The data of the individual countries.
Oh, yeah. Okay, I guess. So we'll have that, and then we'll say, I'm going to do with show because I think that the styling will be easier.
No list.
Okay. Or you can do it with a list. You can do it either way, I think.
Yeah, it just gets sort of buried in there.
Well, just give it some styling. Give it a nice red plot style.
And we'll get rid of the thickness for these other ones and stuff like that.
That's really weird. But that line, I don't understand that fit.
Wait, why is that the average? Let me see. So why is that the size ratio is greater than 100? Oh, because we're not doing because we're only doing the cases that eventually get to over 1,000 here. So if I replace this with this one, then the mean will make more sense. That's the average of that. See, we've got two versions. We've got the version where we do all countries, and we do the countries that eventually reach above 5,000.
Why don't we show that one, the one you've got right now, and then do the thing with countries only going above 5,000 and see how that compares, just to make sure that we know what we're doing here.
Yeah, I'm just going to get rid of this legend thing though, because it's kind of makes it unreadable.
Rerun it without the legend.
Yeah. It already, well, no, it has the automatic legend, which is fine. I'm just, it got rid of the one where it had a legend that like went off the side of my screen. Okay, and then this should be, what were the options we used? Just that. Okay,
that's fairly convincing. That's okay, but now just to understand, hold on, those pictures are actually different. I mean, so the one for greater than 5,000, we should plot those together as well.
Yes, these two together.
Yeah, the aggregated one for the ones that end up greater than 5,000.
Because the scales are different, basically.
Yeah. Okay, so wait a minute. Which is, so the one that ends up greater than 5,000 started off with higher growth rate. This is probably just some artifact of the fact that bigger countries have, I mean, it has to do with that cutoff of 100, I suspect. I suspect if you change that cutoff to be lower, the greater than 100 cutoff to be like 50, that those curves will get closer.
Maybe.
Well, they did.
Yeah, but I mean, okay. Yeah, okay, they did. But okay, I mean, they're still showing the same general thing.
Yeah, which is really interesting.
Exact slopes.
It's really interesting. It's really interesting that's 30 days, basically, from the time when there's 100 cases.
How many countries are in each of those sets?
Let's find out. Well, so actually, you know what we should do? So it looks like there are 10 countries that are greater than 5,000. And in this one, there are probably 80. But you know what we should do? Let's make the plot that shows, because this ragged mean around. We want to show the number of countries. Okay, watch. This is going to be a weird. This is going to be a weird bit of code, but we'll say. 0. Or actually, so what I want to do is I want to plot the number of countries that are being averaged over the x-axis.
Oh, as a function. Yeah, as a function.
Yeah. So basically what we want to do is we want to turn these all into ones, and then we want to, okay, this is the most ridiculous.
So SIGN would work. SIGN.
SIGN. Oh, yeah, sure. Okay, sign, and then we'll just say
pad
right
of the whole thing.
Yeah, and then total.
Right. Okay, so that's the number of countries as a
Yeah. So these are the number of countries that are being averaged.
Right. What's the best way to show that? So this is, yeah, that's a little disappointing, because that's indicating that as there are fewer countries, what is that saying?
So
the various comments on the live stream. Go ahead. Yes.
Well, okay. I mean, so it's something, first of all, to notice is that if you look, so for example, with the greater than 5,000 one, right? Basically, all the countries are in it until day 20, right?
Mm-hmm.
So this is not affecting anything up until day 20. It's only starting to affect things after day 20. And if you look at this curve, most of it is before day 20, and it still looks the same.
Yes.
Right. So I don't think that this is seriously affecting the curve here. It might affect things after day 20, but not before.
Right. Okay. So
for that yellow curve, it looks like there's a slight slope change around day 15 or so.
Yeah, well, this is the one, it's this curve. So I think it's maybe not a slope change as much as it kind of levels off for a second. But I think
maybe
the mean around here, the error bars are pretty big. So I think that may just be that it's kind of uncertain right there.
Yeah.
Well, okay. Do we have data on when different countries implemented different social distancing strategies? I think we were getting some data on that. Does anybody know?
Right. Well, I mean, like, for example, if you wanted to try and read into this thing, arguably, I mean, about 15 days in is probably when you'd expect social distancing strategies to make a difference.
Well, that's true, assuming they were implemented only at 100 cases. And I don't know whether that's right, but okay, let's see. We have some comments on live stream. I think the early countries. Okay. Yes. Is the graph saying better off countries happen to be the ones who've had the virus the longest? I don't think so. I mean, it may be true, but I don't think that this plot indicates that. So Sandra is pointing out on the live stream, the errors in these error bars also scale with 1 over the square root of the number of countries. Is that a true statement? I mean, roughly that's true.
Yeah, I mean, I don't know.
True, but it's not exactly true, because I mean, what it's doing is it's just computing the sample variance, basically, which if I think it depends on the actual values, doesn't it?
Yeah, because if they're all the same, then the error bars will be 0.
Right. So let's ask. Various people are asking, if we remove China, Korea, Singapore, and Japan, what happens? Let's try removing China from these. Let's make that plot.
We'll do the top one, because I mean, generally speaking, though, I think these things about about a few countries dominating on the right side, I think it only works really above like 30 or 20. But below 20, you still get the same looking thing. So we'll just do this, but we'll select max greater than that, and we'll say
how are you
key drop. So you want to get rid of, we'll say China.
Let's drop China to begin with.
Okay. So this is just the big ones.
Right, and can we compare that with the one with China?
Yeah. Well, we'll do this. How about this? We'll show the incremental one just to see how big an effect it makes to remove each of these countries. So we'll start with the one where nothing is dropped. Whoops. You
have a times there.
Oh,
you need a comma.
Okay, that's pretty encouraging. And now let's try getting rid of, note that this is also just a mean of like 10 countries, because we're only doing the big ones. We'll now get rid of like China, and let's try, I don't know, Japan, or let's try Korea next. South Korea. Okay. And now let's try, and we'll just continue. This is arguably a job for like fold. You know what, let's do the fancy way of doing this.
So you need to get the countries sorted in order.
Yeah, well, I'll just write out the countries of interest, because there's a finite list of countries I think people are thinking about, which is not necessarily just the ones with the most.
Japan, Japan.
Tokyo or Japan. So now we'll say we'll just do well, it's not quite fold, really.
What are you trying to do? You're trying to get.
Well, yeah. I mean, well, why don't we just do? Okay, I'll just write it out. I mean, I'm just trying to avoid writing it out so manually, but it's
no,
it's
I
fine.
agree, but you can do that with a fold. Let's think about that. Just a second. You've got
The
a list.
I don't.
fold list, right?
Yeah, but I don't think it's quite fold actually. It'd be fold if we were doing it here. Like this part we can fold. But it's not. So I mean we can do this. But that's not really what we want. I mean, okay, we can do this, and then we can do this. Like this can work. It's just a little bit bizarre. So we want everything we want. Okay, this is an incredibly cryptic piece of code, but this should work. There you go.
Okay, so so the basic bottom, that's very bizarre that it has so little effect. It's very bizarre. I mean, it changes the error bars, but it doesn't change the structure.
Well, yeah, I mean, I think it sort of suggests that well, right, I mean, if we look all the way back, or even just here at the plot where we have this superimposed on the things being averaged, I mean, there are enough things here being averaged, and they're sort of consistent enough. You know, I mean, even if you just look, here they're all up here, and here they're all down here.
Yes.
So there is a definite downward slope.
Right. By the way, a comment Sandra is saying, is it true that the error mean around goes down that square root of yes, you're absolutely correct. I mean, based on the documentation. Okay, well, I actually find this really encouraging that this, but I would really like to know when these different countries implemented their various strategies. It's okay, so scroll down a bit. All right, so okay, now two questions. First of all, I'm pushing a little bit more on the epidemiology side of this to try to understand what on earth is going on here. Why is one seeing this this kind of thing, and can we understand that either from network models or from differential equation models of epidemiology? Any thoughts about this? I mean, this is basically saying that the rate of exponential growth, that the exponent, that the base, this is not the exponent, this is the base, is linearly decreasing.
Yeah.
Right?
Yeah.
And I don't even know that so that means in the differential equation, let's write down, I mean, for the SIR differential equation, right, there would be that beta term, which is, Bob, I don't know all these terms.
Beta times S times I.
Right, but there's the force of infection term. And
right.
What this seems to be saying, if we had a differential equation where where what we're saying is that the rate of infection, I prime or something, am I getting my differential equations wrong? I mean, I prime here would be beta times S, the susceptible population.
I prime would be the negative of that term. No, excuse me. It's the plus of that term minus, well, I use gamma times I of t, which is the recovery rate.
Yeah, but we're not seeing recovery rate here. We're just seeing people getting, but what we're seeing here is the rate of people getting sick.
Right, initially. Yep.
You probably still need to model the recovery rate because you need to know.
Well, this is new confirmed cases. That's all we're looking at. It's new confirmed cases.
Right, but in principle, I mean, right now, most of these places are still a small fraction of the population is infected.
Exactly.
But in principle, you do need to model the recovery rate.
I know, but we're looking at this
right,
case,
yeah.
though.
If we look at just the beginning of the epidemic, then the number of susceptible people is constant, and recovered is essentially, or
right.
number of infected
so what
is
I
0.
think we're seeing is, look, normally it will be exponential because, why is it exponential? It's exponential because, actually, now I'm confused, because the infected, I of t, is, I thought, beta times the susceptible. Is that not correct?
I prime of t is beta times.
Oh no, I see. No. I'm completely wrong. It's I prime is proportional. It's beta times I of t. That's why it's an exponential. I was sorry. I was just confused. So what this is saying is, what I think this is saying is that the beta is decreasing linearly with time. Maybe. I'm not sure. It depends on how that equation
Well, strictly speaking, it will be beta times S times I, and S will be decreasing.
S is not decreasing substantially. The fraction of the population.
So it's basically a constant. You can fold that into beta.
Yeah, right. So it's beta of t. Okay, so take that equation, right, and let's just solve. Okay,
right.
So that equation. If we solve that equation and we start off with I0, well, okay. So that's a nice exponential, a not so nice exponential. It's an exponential we don't want to have as an exponential. But now let's write, instead of beta there, let's write something that is a linearly, so
mx plus b or something.
Yeah, right. MT.
Yeah.
Okay, but that's not, so now we can compute this function here. So this function is the successive ratios. So that's effectively, what is that? That's a logarithmic derivative. What's that?
That's a Gaussian.
Well, that's a Gaussian. I can see that, right? But yeah. I'm trying to understand what is this? What's this thing that we've got here is finite differences up above, right? So what is the continuous analog of that? It's the log derivative, isn't it? In other words, how do we compute?
This is the derivative of the log, because this is just the differences of the log.
Okay, fine. All right. So the derivative of the log there, as Etienne I think has been saying for a while, the derivative of the log of a Gaussian like that would be obviously I mean, yeah, right. It's going to be linear. Okay. So what this is saying is this data would be consistent with a rate of infection, a coefficient of how many people. It's very weird. This is very weird. I don't understand this.
Well, okay. I mean, so a few things. So I mean, first of all, one explanation is that what is this called? This is like the force of infection or something like that. Is going down because there are social distancing measures. And
I know, but why?
This,
but this is suggesting that they're increasing social distancing measures over the 30-day period, which I do not believe to be the case.
Well, no, but it could be that the average number of interactions is sort of going down.
I don't believe it. I think
averages to linear.
I think.
But over 30 days' time is when we see the number of new cases maxing out, and start to, the number of new cases starting to decline is when we generally see that. And it takes about 2 months for the whole epidemic to run its course from the Chinese data.
Yeah, I know. I mean, it's hard to know exactly what to make of that data. I would say the Korean data is more obviously, but that again had a bunch of weird stuff because it was very specific to a particular town and so on. But I'm still trying to understand what this means. So what this is saying.
Another potential explanation would be, if you had, so if you imagine thinking about like the actual network of contact, right? Like if you had the actual graph, one way you might be able to get something like this is if
everybody's
you had
infected their local clique and they don't go beyond that.
Yes, exactly. If you have areas where there's sort of a large fraction is infected locally, which is essentially simulating the sort of later stages of the SIR model, but only locally.
Yes, I understand, but locally, that's very interesting. So I mean, okay, let's look at this. I think this is a really weird result. Okay, so first point is, I mean, I don't think there's I think that type of explanation of saturating local cliques is the most likely possibility. In other words, that at t equals 0 in this plot, whatever social distancing was going to happen happened. That caused the graph to separate into cliques, and then the only place where the infection could occur was inside the cliques. Let's see. Let's just try and model that for a second. Then I want to take a look at some of the comments here on the live stream. Let's see. Let me just look at some of these comments. Correct somehow for the bias of positive reports. Test the neighborhood of a positive individual. I don't know how to correct that, because I mean the testing protocols have been so different in different places. Let's see.
I was going to say, do we have any information, not that I've seen any in the news, of sort of how many tests each country is doing per day?
Yes.
Over time.
Yes, that data exists.
Yeah,
And
that just got
onto
WDR today, I think.
Okay.
When we look at that, but I wonder, let's just have a quick look at a network model for this. So let's imagine, I mean, if you make a network model, I don't know, which one do you think is best? A Watts-Strogatz type model?
Yeah, well, I think Watts-Strogatz, I mean, okay, my opinion on this is, I mean, I think if you have, like, okay, well, we can generate some Watts-Strogatz thing, but arguably, you want to have sort of a more planar graph, because this is like the very local social network. But if you have someone who's like in, say, Chicago and another person in LA or something like that, it's not going to be a small world network that determines how far they are, right? I mean,
that's true, but right now,
the social network.
But it's being broken into individual households right now, and the question is, what happens if?
Right, but so at some level, though, what you care about, right? This would be the network, within a household or within a small group. But at some level, what you care about is actually the I don't know, what you care about is the network of households, right?
You mean because that would change from, because the thing I'm trying to understand is what on earth would give this linear thing? So in other words, if at t equals 0, if the initial rate, the initial infection was some fraction of households have an infection, but then the only growth is by other members of that household getting infected, what does that imply? In other words, if the initial thing was to seed it, it's like seeding a lot of micro countries, so to speak.
So what you'd expect within each household, right? You'd expect to see basically the one SIR model, and then you're summing those up, right? And so that means that you have to take into account the recovered, the susceptible aspects, because those will change. So you'd expect it to be a multiple of a.
Right. So what is the solution? Isn't there an analytical solution to the SIR model for the simple case? We could just sum them.
No, it's a nonlinear model. It's a nonlinear ODE system. So,
but I mean, analytic. Okay, fine. But we can make a simple interpolating function fit.
Sure.
I mean, the thing basically just goes up and comes down again.
Yep.
Over a period of how long? On the order. I mean, the time that. Well, go ahead.
I was going to say it depends on the relative magnitudes of the two rate constants, and we can adjust those so that we have something reasonable to look at.
Okay, but assume it just goes up and comes down again, and assume that you have a fixed set of. So there'll also be a random distribution of sizes of households and things, right? And
Although I predict that's the distribution is, it's one of these that the errors cancel out. I mean, it's like some normal distribution or something.
Yeah, the thing I worry about, though, I mean, what's the average household size that we're talking about? Real households or effective?
It's probably more like effective.
Yeah, so we want something that's probably going to be on the order of 20 or 30 or 40 or maybe a couple hundred people tops.
No, less than that, I think. I think it's less than that.
Yeah,
I don't know what the actual. Well, look, we know from the Singapore data, right? We actually have the picture for Singapore, right, of what the network looks like. Why don't we look at that? Because that was the that gives us the actual size of these clusters. We had that
potentially. Although, by the way, I mean, of course, right? I mean, of course, the households there they were okay. The meetings there were they weren't really households. I mean, they were like conferences and things like that. But I mean, those are the effective.
Seeded things.
Yeah.
But those things aren't happening anymore.
Right, but the seeding events did that. But then after social distancing, you no longer have that. Oh, I see what you're saying. You're saying the initial contagion is from an event like that, But then the question is, why does it decay?
Well, because right. So one of the theories is that basically that most of the spread, probably not all of the spread, but most of the spread is just spread within households or small groups.
Yes. If that, that once there is distancing, one assumes that it's closer to that.
Yeah.
Okay. So, all right. Well, there's clearly some more we could figure out about it. Is there anything else obvious to do with these networks? You were saying, I'm still trying to understand. In this network, if you break the network apart, there was a certain rate of contagion in the full network. Then the network is shattered by social distancing, and what you would expect is
yeah. Well, go ahead.
What you would expect is if you were to make a picture of the thing, you would see little areas of activity, but they're all separate, and it's like forest fires that all kind of burn in a small area and then die out because it doesn't have fuel to go and get larger.
Well, so the question is though, what is the structure of the network of households, right?
Yes.
Because at some level that the structure of you expect that you're going to have some small world network as the social network and as the network within households and things like that, or within small communities. But the question is, I think it seems obvious that it's not, once you have social distancing and things like that, the contact network is not a small world network. It's going to be something else.
Well, right, and I bet the sizes of households will be some Zipf distribution or something. Power law distribution.
Maybe. But one model is if you think it's a planar graph, right? Like if you had it just by geography, that would be a very simple model. It's like we could do.
Right.
We can generate those. My favorite way of generating them is like this, but say Delaunay mesh. Right. So here's a kind of random planar graph. But so the question is though.
I see. So let's look at the growth rate in a random planar graph. I have no idea what that is. Oh no, actually I see. No, I know what it should be. It should be R squared, right? It should be based on the actual.
It should be R squared.
Right.
Because the thing, by the way, the thing to note is if you imagine spread here, or if you imagine an increasing neighborhood here, the kind of the frontier has some very, the frontier doesn't have like a finite dimension or something, right?
It's exponential. Is that true? The growth rate in the Strogat's graph is exponential.
I think so. Yeah. I think that's what we saw last time.
Yeah, I think so.
When we tried this. But on this graph, you'd expect that the frontier, you'd expect it to be some one-dimensional.
By the way, people are asking about the Barabasi-Albert graph, but I think that's less relevant.
I think it's less relevant as well, because the thing about Barabasi-Albert is that basically the thing is that they have a realistic degree distribution, but I don't know what to write here for the second argument. The degree distribution is more realistic, but it's not actually a small world network, really. It's not the actual clustering and things is very weird. And actually, when I was playing around with this before, the results you get with a Barabasi-Albert graph is almost the same for most of these purposes as you get with a random graph, which is kind of not very encouraging. So I think that it's. Yeah.
Okay, but anyway, so the claim would be in one of these social network graphs, there's exponential growth of the volume of a ball, basically, as around a given point, of the number of people that you get to by successive contagion. Whereas in the geographic graph, aka the planar graph, it's like R squared.
Something like that. We can try it. Like if I just say, we'll just make these graphs. And then we'll say, we'll say.
See, I think what's interesting is in this geographic graph, if you imagine an exponentially growing process in a planar graph, it can't it can't get very far because the front, the rate of the front will be limited by it's basically the space available in the planar graph.
Well, right. That's what I mean. So the front here will be some basically one-dimensional thing you'd expect.
Yeah, exactly. Right.
Whereas
in the other case, it's a thing that looks like a hyperbolic lettuce leaf or something.
Right. So I mean, we can just let's look at this. So if we say let's make these all bigger. Let's go to 10,000 or something. So we'll say oh, this is the small world one. So this one we expect to be pretty.
Yeah, that one is roughly exponential. The dual ratios. Let's see whether it's actually exponential.
Well, the thing is, it's reaching the edge pretty fast.
Crazy.
I mean, what's the graph radius?
I think graph diameter is faster to compute.
Okay, well, but it's a different number, so. Well, this seems a bit expensive. Oh, 10. I mean, we were doing it to 10, but I think that, well, right now when we see that, but okay, so if we do this though with G2, weird.
What on earth is going on there?
Wait, why does that? So the reason it's not unreliable is because I pick a different vertex every time intentionally because I think it's a better average.
I think you should pick multiple vertices
at each step. I mean, that's basically the same as saying here, saying table of.
Well, no,
10.
I think multiple initial vertices. I think you should average over a bunch of initial vertices.
Yeah, that's what this is.
Okay.
For averaging over 10, it's average over.
What the heck's going on there? What did it just do? Look at that. Make a let's plot that. Use more vertices. Use more vertices. You're not using more vertices, I think.
100.
And then, okay, so that is in the planar graph, right?
And this is it hitting the edge.
I understand, but why isn't that's the aggregate number of vertex out component? Why is it so? Wait a minute, it's an undirected graph, and you're going n steps in vertex out components. So that it should rise like r squared, shouldn't it?
Yes, but it doesn't.
The
because I think it's hitting the edge. I think the thing is that the graph is not like the graph needs to be, I think, really big. I mean, I'm gonna save this notebook and I'm gonna try. We can try and make it really, really big, but I'm not sure how efficient that will be.
Right. Okay. But in any case, okay. Look, the outstanding problem here. Maybe we should just look at a few more things. The outstanding problem here is explain that linear effect, which really is a quite striking linear effect. Really is remarkable. I mean, did we make any mistake? Anybody on the live stream see any mistake we could have made here? I mean, this looks like a real thing. Let's see.
I mean, one thing to note is that individual country doesn't seem to have necessarily this, like China was not linear.
Well, but they're somewhat. I mean, so this is the plot of things being averaged, right? So I mean, if you look at individual ones, it's a bit hard to see in this plot.
Also, it converges to one, so it cannot be linear all the time, right? It's just like on a small.
Well, no, it hits one and then sits there, because
right, because it can't go below
at one. The critter is extinct, right? And that's where it will. That's the place we want to get to. Okay.
I mean, you definitely do see though that all the countries start around 1.4, and by here they're all around 1.2-ish.
Yes.
So.
Okay, so let's go back down again. I'm really taken with this linear thing, and I'm trying to understand. There's got to be a way to explain that in terms of this graph. And I think it's also important to understand, because a lot of epidemiology modeling is done on the basis of these differential equations, which assume essentially random mixing of people and so on, which is completely incorrect.
Basically a complete graph.
Right. Which in the once one is doing social distancing is absolutely incorrect. And so it would be nice to understand, and it also is relevant if one thinks about ending social distancing in various ways, what one can then expect will happen. Because, if one can first is to explain why there is a linear decrease in the rate of increase, so to speak. And I just think there has to be a graph theoretic way to understand that, and it has to be that the again, let's walk through this again. Maybe somebody can see how this should work. You've got a graph. It is initially very connected. The thing is growing exponentially in that graph. It continues to grow exponentially. I mean, we're still seeing exponential growth. We're not seeing non-exponential growth. It's just that the rate of exponential growth goes down. So the rate of exponential growth would normally be the number of contacts per person, I think. But what is strange is that one would have thought the number of contacts per person, at the moment when social distancing happens, the number of contacts per person might go down from, 10 down to 3 or something.
Although to be fair, though, that this is an average, and so if different places implemented social district, if that was correct, that every place had a big drop off when they implemented social distancing, then you would expect, this could just be saying that
there's another point.
Social districting linearly over time.
Hey, listen, there's another point. There's a 2-week delay, right? So
right, well, sure. So I mean, the point is that if you imagine that every place implemented social distancing at a different time, and the time at which they implemented it is sort of modeled by some linear thing, then this would be the 2-week shifted version of that linear thing.
I'm not buying that. I think they all implemented at a time when the number of cases went above something. I mean,
but the thing is, if you look at this plot, though, I mean, I think that it's not super obvious. I mean, I don't know for these different countries, but there isn't really. It's kind of noisy, and it's hard to tell if there's a moment where it's like, that point, that's where social distancing.
Well, I understand, but there'll be a 2-week delay anyway. But my question,
sure, then the 2-week delay after when they, implemented it.
And that could probably smooth out the effect as well.
Right, but so at some level, the thing had to get to its initial 1.4 or something somehow. We're not seeing that because that's at a small number of cases and so on. But it got to its 1.4 growth rate. Then let's imagine that that the quotes 2-week delay is actually some kind of exponential distribution or something, isn't it? Isn't that the Bob?
This is what the latency period from exposure to becoming infectious, or is this the
I don't know.
recovery period?
No, it's not the recovery period. It's
okay.
Time, because the point is that there will be. The thing is, some number of infections were already seeded at the time when social distancing occurred. So some number of infections were, inevitable at that point, right? Even though people were then no longer able to infect other people, they themselves were still going to, show up as cases when they wouldn't have shown. So in other words, there was a certain number of people who, going into this sort of potential decrease period, there was a certain number of look.
That's the latency period from going from exposed to becoming infectious and symptomatic.
Fair enough, but let's imagine that coming into the beginning of this plot, there were a whole bunch of people who were inexorably going to get sick, right?
Mm-hmm.
They were already infected. They just weren't cases yet, because what all we're seeing is cases, right? They were not known to be cases. So then one thing we could be seeing here is simply there were a whole bunch of cases that came in at the beginning, but they didn't actually show up as cases until a bit later. But a decreasing number of them are showing up as cases 2 weeks later or 30 days later, simply because there actually weren't new cases. You know, there were small pockets that, in other words, that the growth after social distancing started was primarily cases that were already incubating. Is that plausible? Is that a plausible hypothesis?
It's plausible, and also if there's been an increase in testing, you'll pick up more as well. And we don't know how even the testing was in the different countries.
Right, but let's take the hypothesis that, I mean, let's take the extreme hypothesis that everybody became completely 100% isolated, right? So that there was no more contagion after t=0 in this picture, right? And that therefore the only things that are left are people who were becoming symptomatic with some distribution.
Right.
Well, but in particular, though, if this is a line, that basically implies that it's let me see, what would the distribution be? I mean, it's basically just implying that this is showing what the time to showing symptoms is.
Something like that, yes. I mean, because this is saying that, but there's still, remember, there's still growth that's going on here, and that growth, I mean, there's still day-to-day growth. This didn't reach, you know, the steady state would be everybody has shown their symptoms and there's no more growth. That would correspond to a ratio here of 1, right? At the beginning, the thing is growing exponentially with a, you know, daily ratio of 1.4, let's say. Okay, so it's gone into the thing with a you know, a large number of people infected, and then what one's seeing is the runoff. So we should be able to model that. Okay, who's fast enough on the differential equation feat here? Etienne. The okay, so think about this. So we've got a certain number of people, an N0, where are people who are infected, and they are going to show up at a certain rate. And more of them are going to show up at the beginning than later. Right? And the question is now, no, I don't think it's,
or exponentially. I mean,
no, because the rate of getting from infected to symptomatic is, what is that distribution, Bob?
That's just the latency period. It's still going to be exponential generally.
Okay, so you're saying that if I'm infected, then the distribution of times to show symptoms is like e to the minus lambda t. Is that true?
Roughly, words, yeah.
I see. So most people show symptoms. I mean, there isn't. I'm surprised by that. I thought that it took a while for the virus to replicate and actually produce symptomatic effects. In other words, if you get, you know, if you get some virus in you, doesn't it take a few days for it to replicate to the point where you...
Yes, and that's the average latency. And the reciprocal of that is the rate that we generally use to go from exposed to infected symptomatic.
Okay, but what I'm asking is, assume that at t=0, a whole bunch of people got infected.
Right.
What is the distribution of times before they show symptoms? So some people won't show symptoms for a whole week. Some people will show symptoms up, you know, there may be a minimum time of 2 days or something to show symptoms.
Right.
What is the distribution of times to showing symptoms?
That I've never seen, and we've just always modeled that with, you know, the exponential. That it's just, you know, people move from that initial state to symptomatic state based on how many people are infected.
Right.
But how many were there?
But this is showing a different thing, right? Because this
no. It's showing exactly that because
if the sorry. So if it's an exponential,
still, Christopher, you're still caved.
My headset's now stopped working. Hold on.
Can you hear me now?
Yep.
Okay. So Right. So I mean, basically, if you have an exponential distribution modeling this, then this would be the PDF of the exponential distribution is how many people you expect to be showing up at any given, at each time period. And then if you take the log of that, because we're looking at it, the ratios, which is basically the derivative of the log or whatever, then you get something linear.
Mm-hmm.
Do you?
So don't you? I mean, look at this. Isn't this going to simplify to? Yeah.
I mean, first it's a total, right? So it's a CDF. We would.
Sorry. Oh, yes.
Wait. Is it?
This is also something that's going to be.
Yeah.
Well,
okay.
Yeah.
So what do you want to take there? So what is that thing? So that is. You're saying that that's the ratios as a function of t. So what is that? That's
so arguably
take r equals 1 there, and let's just plot the thing.
Well, 1 is not what you want. Let's say 1/7. That's I believe the mean of this is going to be 7. Yeah.
Okay. So that's a 7-day.
We'll make it 14-day because
No. That's wrong because it's.
Okay. Fine. Then 7. So if we say.
Okay. For 30 days. What is that?
No, but we need the derivative of this, don't we? Oops.
Why do we need the derivative? Which is
because we're looking at the differences of the. Well, no. Sorry, we don't. I'm not sure we're looking.
Okay,
that's a logistic, right?
Let's try.
Yeah, that function is a logistic function, but let's just do the basic. Think about it in sort of agent-based terms. Okay, we've got at t equals 0, we've got n people who have been infected. They will have been infected at different times, so they will be at different stages in this exponential distribution.
Mm-hmm.
And then the question is, how many of those people will show up as sick and show up as confirmed cases as a function of time? Right? By the time you're 30 days out, assuming that there will be no new people, because assume that the distribution, it's an exponential distribution with some, let's say, 5 days a week, something like that, as the lifetime of the distribution. Then that means 30 days out, nobody is showing up as a new case. Anybody who's showing up as a new case actually had to get it from somebody who was had to get it as a secondary thing from somebody who was in that initial cohort.
Right. And if you're assuming perfect isolation, we should only be seeing the maturation of the people that were initially infected.
Right, which should be an exponential distribution, I think. Is that correct?
Yeah,
or is the CDF of an exponential distribution?
No, I think it is actually the PDF because we're looking at the change, right? Because this is right at each point here, this is the increase in the number of cases, not the total number of cases.
Yeah, because we're taking the ratios.
So I think we do actually want the PDF.
Okay.
And then if we take the log of that and then plot that, well, I already have it, but whoops. Now it's the log of the log, but yeah.
Really? Well, that would be remarkable. Okay, let's walk through this logic. So you're saying, let's walk through this again. So at time 0, you have a certain set of people coming into this. Those people will then show up as sick with an exponentially decaying distribution. So 2 weeks out, nobody's showing up as sick anymore, right? And that's what. Okay. So now the question is, in the ratio of how many people show up as sick at the beginning, there's still an increasing number of people showing up as sick because those people didn't mature until the exponential distribution, until they were delivered by the exponential distribution, so to speak. And your claim is that the ratio, I'm not quick enough to see this. I don't know.
Right, so maybe just again, here's the way to think about it: is if we have so this is if it's an exponential, if everyone was infected at the same time,
yes,
just supposing that, and then it's just a matter of when are they developing their symptoms, and if we're supposing this is an exponential distribution, then with a mean of like a week, right? Then this is the plot of for each day, how many people do we expect? Well, okay, it's approximately for each day, how many people do we expect to find as a new infected case?
Okay, and the total number of cases is the CDF.
The CDF, right? But this is right. But this is the increase. This is for each day, how many new cases do we think we're going to find?
Right.
Yep.
Right. Okay.
Okay. And so then if we take the log of this, because that's what we've done up here, because we're it's exponential growth, we want to take the log, then you get this.
Right. Actually, NJ pipe organ on our live stream is pointing out there really should be log of PDF over CDF, but that's going to be really close. Okay, so in fact,
wait, why should it be that? Or is it because wouldn't that be if we were looking at the? Oh, you're right. Yes, you're absolutely right. I guess we can do that. Yeah, that's a good point.
Okay, but I mean this is very interesting. So I mean it suggests. I'm a little surprised that I guess I don't know exponentials well enough somehow that 30 days out you could still be seeing the tail of the distribution for a t=0 for a population that was only seeded at t=0. I guess that's right. I mean, I don't know. And that you don't have to have secondary transmission to still get new cases 30 days out. Seems a bit surprising to me. Okay, well, so we have a minimal model for what's happening in that will make that picture, which is basically that the dominant effect is cases that haven't yet showed up, rather than some additional contagion. Interesting. So then what happens if that is the correct model? You kind of have to wait long enough that, I mean, it's just like quarantine. You have to wait long enough that it's really died out in each of those little isolated cells, because otherwise it's just going to start right back up again.
Yeah, yes. Well, the thing that's difficult is you're basically trying to say when is the tail of this reached actually 0?
Yeah.
Right, and that's kind of hard to know when it's reached actually 0.
Well, yeah. Right, but that's why case tracing and all that kind of thing is important.
Yeah, or doing a stochastic simulation to try to understand.
Yeah, but it's not going to help because there isn't, there's no herd immunity. Once you seed it, it's going to start growing. So unless you isolate each individual case, there's no way to stop it. If there is, I mean, you're not going to reach actually 0. Not in a country with populations of tens to hundreds of millions.
Mm-hmm.
Okay.
Well, but the pockets aren't that big. I mean, if you're talking about pockets of infection, those should die out.
Well, so long as they're left as pockets, but as soon as the pocket can spread into the population at large, that's not going to be true anymore.
That's right. Yes, again. Yes.
But the question is, how long do you have to wait to let the pockets actually die out? And that depends on whether there's secondary transmission, because if there is, then the virus survives by hopping from host to host. Once the host's immune system has kicked it out, it's got to go to another host.
Right. And the pockets, while they might be isolated from one community from another community, and there's no migration between them, there is still a chance you'll get the secondary infections within that community, which is just going to extend the lifetime. Eventually it will die out.
Right, but what you're basically saying is, in the SIR model, the SIR model is a continuum model. So it only knows about the rate constants associated with transitions between these different, and that is an incorrect model for a group of 10 people, for example.
Exactly.
Which is dominated by essentially what you're referring to as stochastic effects. And so a question would be, in what is the discrete analog of the SIR model appropriate for a group of 10 people? And what is the distribution? If you ask, given a size of number of people, n, what's the distribution of times to die out as a function of that number of people? Because presumably the SIR model has a certain implication. I mean, it's like a little cellular automaton type thing. It just says it's that model in terms of its quotes physics, its biology, whatever, its underlying rules has some assumptions about the probability that somebody's going to get sick given that they're susceptible and so on. I mean, and also, isn't it the case that the SIR model basically assumes everybody is going to get sick, doesn't it? I mean, in its simplest form, it basically assumes, isn't that the case?
If R0 is greater than 1, yes. If R0 is less than 1, then no. Not everybody gets sick.
Right. If R0 is less than 1, the thing's going to die out.
Right.
But I mean, right. Okay, fair enough. Let's see. Is there anything else we were going to do here?
So one thing, by the way, that you could look at, I mean, if you want to know if this is correct, is if that Singapore, the graph data, if it had for each case, because it has, the sort of context of infection, like, oh, this is a family member, or, oh, there's close contact. If it had when that close contact was, then you could look at the distribution of times between when there was, sort of infecting event and when they became a case. And that would kind of tell you
very interesting.
whether that's an exponential distribution.
Does the Singapore data have that? Can we look? I mean, we can just
we can look. Let me see. I can try and look, but it might take me a minute.
Okay, but actually, let me look at some of the other comments here on the live stream. Let's see. Right. The curve of delay in testing could be modeled from Wuhan since January 24th. I'm not sure about that. Yeah, it'd be really good to have the dates when the countries increased, did the social distancing thing. Can somebody find out whether we actually have that data? I mean, there was a claim that we were getting that data like today. Somebody here tell me whether we actually have that data. Maybe
I thought it was the testing data that came online today.
Okay, question from Brian here about RNA viruses and high mutation rates. Actually, there's a person called Trevor Bedford who has this thing called NextStrain. Trevor was actually, long ago, was an intern with us, and actually was helping us quite recently with biosequence designs. But he has a nice website and a research effort in Seattle, working on exactly that question of what all the various mutations have been, and has very interesting genealogical trees of how many mutations there were. But I think it's I think this is a 29,000 base pair virus, and I think it's like is it 1 or 2 mutations per transmission event, something like that. And from that, you can make deductions about sort of how big an iceberg of undetected cases there are, because you can see, given the genomes that have been picked up, and I think there was just some new genomes picked up from Singapore in the last couple of days. And so there may be some more information about that question of how many, assuming a certain mutation rate, you can work out essentially how many people, given that you've detected some number of people who are sick, how many people it had to go through to get to those different people. And I think I think the indications from that were that, I mean, Trevor had some estimates of like the total number of people who were infected in the Seattle area that were not hugely large. And I don't know how that's actually panned out in the last week or two, whether those estimates have turned out to be correct. Let's see. Question here, has anybody made an analysis of relation of infection hotspots to air quality? It's a good question. I wonder whether we have air quality data anywhere. I think we certainly do for the US. We certainly have extensive air quality data, but I don't think that's I honestly don't think that's the place where that's going to be the biggest effect. I have a suspicion that there may be a different effect, which is in places where there's air quality problems, people are used to wearing masks and have masks, and I would suspect, just on the basis of common sense, that that makes a big difference to a respiratory virus and its transmissibility. And so, you know, there may be a couple of different things going on there. I mean, one may be, you know, sort of gunk in one's lungs from bad air quality, but another may be wearing masks because there's bad air quality, which may reduce transmissibility. So I don't know exactly how that would go. Okay, let's see, a comment here, the drop of daily growth corresponds with infection count. Okay,
I think
that's nice.
that's fitting this. I think that's fitting
okay,
this
that's
curve.
nice. That's nice. Okay. Oh, that's a good point from Brian on live stream. People wearing masks tend to touch their faces significantly less often. It's undoubtedly true. Well, and not least because you've got a mask there and you can't do it. Okay, let's see. Were we looking for? We were looking at the Singapore data. Did you find?
Yeah, I mean, here's the graph, and then here's the edges. But I mean, this is from this aggregation of the raw reports from Singapore, and these don't appear to be annotated with dates.
But those case numbers can actually, the Singapore Ministry of Health don't they have the case numbers?
Actually, that's a reasonable point. So you can tell by the case numbers.
I see, the ID of the number of the case.
Right, because that basically tells you when did this person become symptomatic, and this tells you when did the next person.
Okay, so
notice that some of these are backwards, as in they found this person before they found this person.
Oh, in other words, they were backtracing from one person. So the serial number of the case may not, but why don't we look on the graph? We can annotate it. We have the case numbers on the graph, put the case numbers on the graph, and then simply look in the flow and the graph, just see whether there is in fact a tendency to go from lower case numbers to higher case numbers.
Sure. Well, okay, I propose the way of doing that is to say, we say, we get the edges, and we say for each of these, we'll say we want the from and the to, and then we'll say
that has cluster numbers as well as case numbers.
Yeah. So we'll first get rid of the missing ones, or well, let's just do it like this. Okay, we'll do that, and then we'll say select all true of. Oops. Okay, and then we'll just say.
You just want to get rid of first 5 letters. String delete, string drop.
Yeah.
And then you want to do to expression. I think you have to map it. Actually, you've got to map it at level 2.
I think it's partly listable.
Okay. And then to expression.
Isn't there a new function that's like to expression, but it's safer?
Yes, there is.
What's it called?
I should know. bad sign that it hasn't
No,
been
no.
advertised enough that we know what it is.
From number string?
Is that what it's called?
I'm guessing.
No, don't put it in there. I don't think that's correct. Okay, in any case, we've got to expression. There's
Yeah, okay.
somebody should report the fact that it's not linked from to expression. We're not getting the correct thing.
We're not getting it. Okay, so then what we want to see is if we just see
I'll just do a list plot of that, and let's just see whether.
Yeah, okay, sure.
And then we just see whether it's.
I'm gonna put
Okay, so what is that telling us?
Good sign.
It is a good sign. Yes, most things are to the right of that. So that means that these are mostly they're mostly increasing. Okay.
Yeah.
So now what this is showing, actually, that's pretty interesting. Look at that.
But there's a pretty weird set. I assume these are clusters. Well, no, because there are no clusters in here. But I assume that maybe after.
Wait a minute. Just take all those numbers. Just flatten the whole thing and just check that all numbers are actually there.
They won't be, because a lot of people got them from clusters, which we deleted, and they got them from unknown, which we also deleted.
I see. We might want to index this. So these numbers might have been, because I mean, otherwise it looks like there are waves of infection there, which would be totally weird.
No, but I think what that really is it's probably just that there's a cluster which infected a bunch of people, and then we don't count those, but then those people all infected a bunch of people. Right, and so then we do get a wave effect from each cluster.
Okay, but so what we want to do is turn this into an index number where we have ignored those. Is that right?
I mean, at some level, this is what we want to do. The first one minus the second one.
Okay, but then so the issue is what we're trying to do is we're trying to find out what is the distribution. We're trying to find the distribution of this number, of that number that you're computing there, but after we have squashed out anything that is purely an artifact of the numbering scheme.
I'm slightly confused though, because we're doing from and then to. So, okay, so wouldn't we expect this to be mostly negative based on this? Wait, why is that positive? Because we expect the from cases to be lower than the to cases.
Well, let's see some specifics.
Wait, no, this is showing the opposite. This is showing the opposite of what we were saying. This is showing that the from cases are lower than the to cases.
Oh, that's bad news.
These are the index of the tracing, right?
Well, it's the index. It's I don't know if it's the tracing.
No, wait a minute.
It's just the index
if from
of the
is less
cases.
than 2, that's good. Which way round is it? Is it
so it's from and then to? From and then to. We want from to be less than 2. Basically.
Yeah, which it isn't in this case, apparently.
Yeah, they're all.
So they're mostly so. Okay, so what that's telling us is that in the Singapore data set, mostly. Oh, I see. That's actually not surprising. Somebody comes in sick, and then they say, "Where did you get it from?"
Yeah.
It isn't the case that somebody has come in sick, and then they say, "Who did you give it to?"
But interestingly, if you look at the distribution of how different they are, so a bunch of people it's pretty close, where it's like they find a sick person and they quickly find the person, they trace it back. But then there's some cases where it's like much later down the line. I mean, there's some of these like case 94 got it from case 1476.
What does that tell you about this distribution? It does tell you something, because case 1476, hadn't showed up at the hospital, presumably, until considerably later. I mean, that's actually a very weird thing, because one would think if somebody got it from somebody else, that the person they got it from would actually be sick, unless they got it at the point where that person they got it from was asymptomatic. Right? I mean,
but then you think that they would test them very quickly. I mean, especially in Singapore or something, you'd expect they would test them very quickly. Right, like if you meet someone.
No, I understand, but if they knew who it was from, because they might have just said, "Well, I was hanging out. I went to school that day, and there were, 1,000 people in the school, and I don't know, who I got it from." And then, they will only have tested close contacts. And what that's suggesting is that, I mean, if I'm understanding correctly, that's suggesting that there was a person who was not yet showing up sick, therefore was not yet symptomatic, who was eventually found to be the cause for somebody who did show up as sick, which is kind of weird, right? Because you would expect that as soon as somebody shows up sick, having had a 1-week incubation, that whoever they got it from is already sick. Bob, am I missing something?
That makes sense. That makes sense.
So then that's
and
something
they
very
should have been picked up already as, from reporting to a hospital or something like that.
Unless, for example, and here's a question, unless the distribution for this particular disease, unless the distribution of times to symptoms is very broad. In other words, if it could be 3 weeks that somebody is infected and infectious, but not symptomatic.
Yeah, and I have no idea what it is in terms of becoming symptomatic. You know, how that maturation occurs.
By the way, I think that we just got the
well, let's have a quick look at that.
Got this here.
This is the testing.
I'm not sure.
Pandemic
measures taken.
Okay, well, let's take a look at it.
Yeah.
Open up basic examples. Is there anything there? Yes. Okay. See if you can copy that.
Sure. Okay.
Okay, that's just privately deployed so far, not yet in the.
Okay.
But there's a comment, a very biology-oriented comment on the live stream, which I don't understand well enough, about glycoproteins and things. I don't understand this. Bob, you might look at it.
I don't have the live stream chats. Has somebody posted it to Twitch chat?
Yeah.
Oh, here it is from from Jump Out.
I translate that biology if you can. Not sure.
So, okay, so I mean, obvious, a quick thing to try. So there's 2 quick things to try. First of all, let's just try the obvious thing.
Oh, that's very interesting. Okay. So that's that shows, hold on. So that is telling us, go ahead. Yeah.
Well, okay, the next thing is to look at when a country goes over 100 people and then see how long until they implement various things.
Yeah, let's do that. Let's compare the country going over 100 and implementation date.
Yeah, so what was that called? We had country TS. This is the main thing. So we want to see what is the first date where it goes over 100. Let's try this. And we'll say, oh wow, I didn't know it did it like that. Maybe we'll say no. It's because I did path. There's another one that's called like date or
What you want is date list and value.
There's a thing that does this.
Date path. It says there.
Okay. Okay, and then we'll say just is there a, well, okay, I guess I can say select first. And and then we'll say, or we'll do this, and then we'll say delete missing.
And then you want to get rid of your selector there. Okay, so that says when each country went over 100.
Yeah. So first of all,
well, let's just do the date histogram of that.
Okay, and now what we want to see though is we want to see government measures grouped by. I'm just going to totally guess that there's a field called country. Okay, and there is. And then we want to say country, comma. Why don't we do this? We'll start with and let's just say.
That's wild. Is that going to work? Do you think mean around for?
Does mean around work for dates? Let's just do mean for now. Does mean work for dates? I think it does.
I don't know. I really don't know.
Actually, I've never tried it on dates. Let's try O100. Because no, division doesn't work. So we'll do. But we can.
That's actually an interesting thing. Could somebody make a note of that? It's an interesting thing to make work. Mean with dates. Don't see why it shouldn't work. I mean, date histogram works, so why can't we do other date operations?
I mean, you should be able to do mean on the absolute times, and then potentially convert them back.
Yeah, that's what we're doing right here. Why does that complain?
You might get a complaint about granularity, though, that they can't be combined. But
I think this is the problem is that there's some implementation dates that are missing. Maybe. Let's see. If I just do government measures of all, comma, and I say.
Stephen, I think what this person is suggesting about the peptidase and glycoproteins is attaching a peptidase to the glycoproteins in the host's cells, so that when the virus shows up, the genome of the virus. Well, actually, no. This has to be. No, it doesn't make a lot of sense. I'm not exactly sure what he's trying to say, but I thought it sounds like a way of preventing the host cells from becoming infected and therefore machines to produce more viral genome, more viral particles, which has to happen inside host cells. But it doesn't make a lot of sense here.
I don't understand yet. Okay, clarify if there's some.
Is there no 2 Unix time?
There is. I think it's just called Unix time.
Oh. I don't totally understand why this is doing this.
What are you getting from?
Oh, there we go.
Okay, now you've got to turn that back. That's going to be a little tricky. I mean, if you just did mean.
No. I'll just do mean, and then we'll just do.
Okay.
And now I'm going to say normal of this.
And what's that going to give you? That gives you the average time.
Implementation time. So this is about when measures started to get implemented.
Oh, that's cool.
Maybe we should do median, actually. Well, we'll start with mean. And then we'll say merge. We'll put over 100 on the x-axis. And so those are some dates. And so actually we want to say we'll do it like this first.
Just to compare
2 things
them.
we should do. Yeah, and then we'll do the difference. Date object missing indeterminate.
Well,
so
that's because
are some missing.
Yeah, don't worry about it. Just plot that. Just plot that with a tooltip for each country. Let's just plot that just to compare them.
Complaining a little bit.
Okay, so now.
And now we need the line. We need the line.
That's a cool way to make a line on one of these plots. I hadn't thought of that.
It's kind of, I think it's the way to make a line, but okay. So
okay,
this is over 100. This is measures.
So in other words, the countries to the, let me understand this. The countries, what does this mean? This means which countries didn't implement measures until they went over, which countries implemented measures before they got to 100? So you're saying, for example, India, it looks like from this, implemented measures before it got to 100. Is that correct? Or their average time of implementing measures?
Yes, exactly, yes.
Okay. Whereas, like, well, that's pretty interesting. Hold on.
Wait, let me clean up the mean implementation time thing, because there's some missing. There's this missing stuff that's hiding in there. I already have that delete missing. I'm not sure totally why it's date object of missing indeterminate. I don't know why that could be missing.
Because there was nothing in the mean. There's nothing to take in the mean. That would give
no, because it's mean of no. Has means behavior been changed? No. I don't know where this missing of indeterminate is coming from, to be honest. But maybe we want to say we get those means.
And we've got indeterminates, yeah, there. So you've got to delete missing.
Yeah, we'll select. Oh, isn't there a number? Okay, and then we'll say, okay, and these should all be well behaved.
Okay. Okay.
Now we can also say,
okay, so that's in days, and what's that showing us? That's showing the difference in time between the mean implementation and somebody is commenting. Find out what the /@ syntax does. Christopher, just show people what /@ does.
Oh, okay, yeah. Let me just. This is probably the most. Okay, this is probably the single most obscure infix operator. So first, you've got there's f @*.
No, just show @ first for people who don't know.
Okay, fine. So there's there's @, which is just a shorthand for writing function application. Then there's, and you can sort of nest these like this. Then there's @*, which is function composition. So if I have something like this and I apply it to x, it turns into f of g of x. And then we have /*, which is exactly the same as @*, except that the order is reversed. Right. So
maybe
if I wrote,
yeah.
And the point of this is just that, I mean, this is in some contexts more intuitive, because basically this is how you'd write it with @, and so that's kind of the intuitive order. But then this is sometimes more intuitive, especially with data set, because basically you're applying this function first and then you're applying this function. It's nice that it goes left to right. And also the reason why it's / is because this is analogous to another syntax, which is you can do stuff like this with //, which is the equivalent. It's the postfix version of @. But yes.
Right, let's go back to our data histogram. So what this is showing is that some number of countries implemented, the minus numbers correspond to implementation of measures before they reached 100 cases.
Right, so this is, okay, if you're to the left of this red line, then that means that
You were ahead of the game.
Mean
You implemented
implementation time was later. No. Your mean implementation time was bigger than your over 100 time.
Okay, so show us
behind the game.
In the scatter plot, which countries were slow?
All right, let me label the axes because it's too hard to tell. This is extremely hard to tell what's going on. Okay, we've got over 100 and okay, so if you are over 100 really late, but your mean implementation time is early, that means you're ahead of the curve.
Okay, down in that corner. So that means
this is ahead of the curve.
So Turkey implemented things early, and what's the country at the very top of mean implementation time? Oh, that's very recent. So they only implemented very recently.
Right, but they still don't have that many cases. So actually, another interesting thing is if we change this over 100 to be over, some other number, 50, then does this change? I mean, or does this move the line? It'll certainly move the line.
Yeah. Well, I think the other thing, keep a copy of that picture, and let's change it to, instead of the mean, let's change it to the min of the date. In other words, the first measure that they implemented.
Okay. So we'll try that. We'll try min implementation time. Also, I just want to quickly try median. See if it looks different from mean. Maybe a little.
Yeah.
But no, not seriously. Okay, so then we have min. There's a whole gaggle.
Well, what does that mean? What does that mean here? So those are. Well,
that just means that they all went over 100 around the same time.
Yes.
And they all implemented things around the same, or actually no, they implemented things around the same time, and then they sort of went over 100 in also some time.
Okay, so wait a minute. So the first countries to go over 100, so China must be to the left of all of this stuff. Maybe off the plot.
Yeah, because look at the range.
Yeah, okay.
It's an absolute time. So if I say plot. But also, I think the data starts actually pretty far in. Like, I'm pretty sure.
Yes, I think they were at 500.
China, they were up over 400 when they started.
Right, so this is not the real over 500 for China.
Right. Okay, so what is this telling us? This tells us that Italy, for example, implemented, its implementation time was quite rapid compared to, whereas here, like the UK is showing implementation time. Yeah, so what?
Their first measure came after they had 100 cases.
Right. Okay.
Just out of curiosity, what is each country's first measure?
That's a good
is it
question.
Like checking temperatures at airports, or?
Yeah. No, that's a good question. So let's look at what this government. Just the first two rows. So measure. Okay, so we'll get the group by country.
Somebody was asking to make that plot we just made, but without absolute times, with actual times on the axes. Is that easy to do?
You can do it on one axis.
Yeah.
We don't have a date list plot.
No, but why not just have isn't there a way to change to have a ticks function that just changes it?
Oh.
Yeah, you'd have to do frame ticks and.
Okay, no, do ticks.
Well, okay, this one is ticks, yeah.
Yeah, because it's not frame. Func. Oh no.
Okay, go to the docs for date list plot. Take the first example. Evaluate it. Do options of. Okay, so go ahead.
Oh yeah. I see. Yeah.
options of that, pull out, where's frame ticks? Pull out that charting backtick date ticks function.
Oh my god.
Blah, 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 blah.
This is horrendous, but okay.
So we'll do this, but we'll make it ticks.
I mean, you only need that charting backtick, thing.
Do I not? Can I just put it like this?
Yeah, that should be fine.
Only on the bottom though.
Wow.
No.
Take out the ticks labels none. Yeah.
Okay.
Okay. I mean, that's actually not too bad.
Try an aspect ratio automatic if you haven't.
That's a good idea.
And Brett, you should make that be a string option for ticks.
I'm hoping to have big changes in store for ticks. So.
Wait, so hold on though. Wait, what is this epilogue? What does this mean?
I mean, that's still...
No, that's correct. That's still showing, because that's relative to the absolute times. That's still showing when...
Yes.
This is showing
today equals today.
Right, it's starting a million years ago, or 40, 50 years ago at this point, though. But yeah, okay. We should do let's add these.
But actually, people are asking what to look at. Well, first of all, let's look at what measures were applied, and then let's look at when quarantine was applied, if that's one of the named measures.
Sure.
Because that's going to give us.
By the way, we might want to just plot the scatter plot of first measure versus number of cases at first measure, or just the distribution of number of cases at first measure. But okay.
Yes, that would be interesting.
Okay, so we'll say.
This hasn't been made. It'd be nice if this was. Well, we'll see.
Let's try this. Let's try measure. We'll look at category, but first let's look at what?
I think you want double brackets.
Yeah, I didn't need to do double brackets. Okay, so there is a quarantine one.
Right, which is the most common one. Wow. Okay.
Okay, let's try it. So this is so we'll now try, instead of mean implementation, we'll say how do you spell quarantine? Wait, do we want to copy position to clipboard? That's what we want. So we'll say
it's right there. Oh, I see.
No. But we want to say let's do this. We'll say, okay, let's write this again. Actually, no, we'll do this. We'll say government measures of select this. So here are the quarantine, all the rows about quarantine times, and we'll say we want the country and the and actually we're going to want to do it. Well, okay, we'll do it like this. Okay, and then we'll say how can Austria do this 4 times in like the same day mostly?
Is it done for different regions, like New York State versus Illinois?
Oh, that's very plausible.
Yeah, which might be why there's a lot of quarantine policies.
Administrative division. Yes, you're right. You're right. Let's just do first quarantine, or we can do mean quarantine time. How about? I don't know. I mean, I think we'll try mean quarantine.
Try first.
Yeah, I think first is more likely because the first. Well, yeah. I mean, if they had an eruption in some particular, like presumably in Korea, didn't they have it in? I mean, did they quarantine Daegu before they quarantined? I don't even know that they've ever quarantined Seoul. I don't think they have they? I don't know. Not been paying enough attention.
Actually, we don't need to say this at all. We can just do it like this. Okay, and we'll say
okay, so that's the first.
So we delete missing, and there's some that are an empty list. So we want to get rid of the countries that never implement
quarantine.
Yeah. Well, I don't know. I'll just do min, and then afterward we'll say normal, and we'll say select date queue. Oops, date object queue. Okay. So this is the.
Okay, so that's the distribution. So let's just do a date histogram of that. That's the time for quarantine to quarantine. Maybe, yeah, that was going to say, let's do it by the day. That's very interesting.
What happens if we do, there's no mean? I can say,
what is that doing?
that's the mean quarantine time instead of the.
Instead of the first quarantine time.
Yeah.
So that's a mean relative to the where if they had multiple quarantines within a country.
Yes.
So that means that, wow, the world closed down in a single week, basically.
Basically.
Wow.
Yeah.
So now let's look at, first of all, over 100 versus.
Can we see the histogram for all the quarantine times for the US?
We can try. Let's see.
Don't get rid of that. Copy that whole thing down.
It's been copied. It's been copied.
No, I know, but copy it so that it isn't confusing with respect to the quarantine time for countries.
Well, we're gonna just hold on a second. So we'll say this, and then we're going to say. That doesn't seem right. Or are there places that have had? Oh, wait, what does quarantine policies mean? Does it mean stay at home? No, I assume not. Maybe it just means like people who are sick should be quarantined.
Well, that's possible. Let's go look at let's go look again. Okay, first thing, let's look at the actual measures. Just make a word cloud of the measures that are in there.
Okay.
Strengthening the public health system. One wonders what on earth that means. Okay. Huh.
General lockdown. I think that's what we're thinking of when we're thinking of quarantine.
Yeah, and I don't know what quarantine policies means. It might mean something very minor. Well, let's look at let's just look at general lockdown as an alternative to. It was a lowercase l.
We'll call it lockdown times.
Okay, now let's do the.
Okay.
Okay, let's find out.
If we look at what countries.
Okay, but so the US, for example, is not in there because it's only state by state.
But for a bunch of these, like for Austria, it was going administrative division by division. So I think this might be a little inconsistent.
Right. Okay, well, so let's go back. I mean, the original thing we wanted to figure out was what's happening here.
So I'm just looking at to see what the measures for the US are, if it knows of any.
Not very many.
Yeah, I mean these are all federal things.
Right. So we'd have to have a separate data set for the for statewide.
Yeah.
Okay, but so the question that we were asking here was, given, so what the, okay, first point is, if the time to go over 100 cases is well correlated with the time to adopt these measures, then our t equals 0 will be consistent between countries. Right, so in that plot where we're looking at, if we scroll back up, and maybe people who are just joined us didn't see this, scroll back up to the most interesting plot as far as I'm concerned. That plot there, the one you just passed.
This one.
Well, that one is a good start, yes. So that's the daily case, the daily ratio of new cases showing a decline over a 30-day period, and we've been trying to understand what the origin of that decline is. That's the averaged over countries. There is a decline of the new cases by day over a 30-day period, and the hypothesis has been perhaps what's happening is that once you reach 100 cases, you implement enough social distancing that you are no longer getting at least many newly transmitted cases, and you are merely seeing essentially the maturation of cases that already existed. And that was if it was the case that 100 cases was perfectly correlated with when social distancing measures were put in place in each country, then that would be, then that would be the thing we would be looking at. If that varies, it's a little bit more complicated. We should, yeah. So we think this is roughly a measure of R0. Yeah. The question is here.
It's a measure of R0, though. The x-axis here is days since there were more than 100 cases in the country. It's by country. So basically, right. It's a measure of R0 as a function of how long it's been since you've gone over 100 cases.
Right. And go ahead.
Well, okay. I mean, so there was one theory that basically that this is explained by, if you imagined that quarantine procedures and stuff like this, or lockdown procedures, were 100% effective, and that all the new cases were just people who were previously infected and were asymptomatic, then you would expect that kind of the distribution of incubation times would produce this line. And so then, if apparently in some of these SIR models and things like that, they assume an exponential distribution of distribution times, if I'm not mistaken, or of incubation times. And then if you work this out, then you get something that's basically very close to linear, which is sort of what we're seeing. But right. But so yeah, and so now we were just looking at the influence of government measures on.
That's an interesting point. So someone's pointing out here that this plot would imply that every country would have a certain number of infections in the end after a month. Why is that?
Wait, no. I'm not sure about that. This is only talking about the ratios of the number of infected people, right? So it's just this is the R0. This is the daily R0.
No, I know, but you're summing essentially a series of exponentials, right? In other words, what you're doing is you're saying this thing, if you look at the total aggregate number of cases, eventually this will hit, this will hit 1, at which point there are no new cases. So what you're asking is, what's the integral? What's the sum over all of these? This ratio, this is the ratio per this minus 1 gives you number of new cases per day compared to previous day. So there is an integral of this that should give you the total number of cases that will develop after you get to 100 cases.
Right. Yes. I mean, it'll be very influenced, by the way, by how much over 100 cases you start at. Because if you're at 150 or something like that, because it's exponential,
I mean, because of the exponential, sort of all those little variances are going to add up significantly.
Yes, that's for sure.
Right. Like this little wiggle where it goes down, I mean, within this error bar, where it goes down, by 0.1 or something like that, that could be a huge number of people in one country and not a very big number in another country because the populations are different and stuff like that.
Well, but those numbers aren't per country. I mean, it's not based on the population. Right. I mean, it's based on.
Yeah, we're just counting one country per. One country is weight 1.
Right.
I mean, but I mean, what the person in chat was commenting, I think, is sort of borne out by the totals right now. Right. What the maximum is China at 80,000, 90,000, and Italy and the US are roughly at about the same total number of cases, despite large numbers, large differences in the total population.
Well, so what claim are you making there? That the thing, I mean, that is a surprising fact in its own right.
That does make sense. I mean, first of all, you should sort of leave out China because China's timeline has been very different because they started much earlier, right?
Right.
But of these places, of all the places that when we looked at this is I think the first plot we made, which is just sort of or I think we got rid of it. I mean, if you just look at dateless plot of country TS, right? So this would be the number of cases over time for every country. What's it complaining about? Oh wow. I'm not sure why that was complaining.
What was the message?
I didn't see it because it was slowing down my front end because it was but I mean, let's just try saying take largest by total. Does total work on a time series? Yeah, but we should actually do hash of last.
Last value.
Last value. Yeah. Okay, so this is the top, or let's take the top 25. I mean, I'm not sure, and we'll set the range to all. So I mean, the point is though is that right now these are all still small fractions of the populations of these countries, right?
Fortunately, yes.
Mm-hmm.
Right, and so the point is it is sort of.
I see. What you're saying is that is that the thing is like it is it's a thing that's growing into an infinite reservoir, so to speak. And what you're mostly seeing is its intrinsic growth rate, not anything to do with the size of the country. I mean, you might have thought that there would be a larger number of seeding events for larger countries, but that may not be the case. The number of seeding events may be quite small. And that therefore it's just like on the order of one seeding event expanding into a sort of infinite reservoir. Okay.
Right, but I mean, but that comes back to sort of what the plot above it is, sort of saying that because all of those curves are roughly the same based on 100 to 500 as the starting point, that I mean, you aren't seeing growth proportional to the population.
Right. It doesn't know how big the population is. The only way it would know how big the population is the number of seeding events.
Right.
Okay, so a question on the live stream is, does this plot tell us the duration of infection? Does it give us an indication of that?
I don't think so, because we're only looking at the number of confirmed cases, right? We're not looking at looking at anything about.
But if it is in fact a reflection of this exponential distribution, it tells us the lifetime in the exponential distribution.
Well, but the lifetime that's the exponential. Excuse me. That's the exponential distribution of incubation times, like time to be symptomatic.
Yeah.
Right after becoming infectious.
Okay, but even that is then what does that imply? Let's just translate that, because we know that this plot is going that the slope of that curve should be telling us something about the lifetime, as in exponential lifetime, as in, or the half-life or something of the time to become symptomatic, right?
Yeah, the half time. Yeah.
Yeah. Sure. Okay.
So what does it tell us
for the incubation time?
Right.
Well,
so
let's see. So the slope. We have a
time?
fit. We have a fit. Where do we have the fit? There's a fit somewhere.
Yeah. The question on the live stream about the duration of infection, maybe we can get that from a difference of the confirmed cases curve and the recovered cases curve.
Yes, which we haven't looked at all the recovered cases curve.
No.
I mean,
maybe that's for another time.
How many people are tracking recovered cases accurately, though?
I don't even know what it means necessarily to be a recovered case. I mean, are they measuring IG? I never remember which one it is, but is anybody
one of the
measuring?
IgGs, but I don't know which one. I
mean, the other thing about recovered cases is just that there's a lot more because the number of cases is growing very fast. There aren't very many recovered cases.
Well, I mean, and the thing is my understanding is that a recovered case is 2 negative tests following a positive test. And I don't know how many countries or bodies are dedicating test cases to.
Yeah, dedicating tests to testing for recovery as opposed to being clinically asymptomatic.
Right.
Mm-hmm.
Okay. Well, got a fit there.
And there was also a change in being declared a confirmed case from being tested positive with the antibody test as opposed to being clinically symptomatic. And that's why there was that big jump in the Chinese data, the China data, when they threw in all of the people that were clinically symptomatic as well.
What units is that in? That's in units of inverse days or something?
Well, it's a fit of it's a line that's fit on the ratios of.
Right. So it's ratio. It's the fit. That ratio is the exponent. Right. So it's a fit of the exponent in units of inverse days, I think. Right. So if we take that, so one over that. Yeah, 1 over that.
That's not right.
That's not right. Presumably that's not right.
That's not right.
Absolutely.
No,
weird.
That's 3 months.
Well, I know.
It's definitely
totally
not
weird.
right. Because there isn't 3 months of stuff here. Now, hold on. I don't think that's quite what this is. So this is, so this is the. I mean, you also have to. There's also the B part.
Why is the B part relevant? That's just shifting the thing.
Yeah.
I mean, the 3 months was right for the slope.
Is it? I mean, so what is this?
Oh yeah,
number?
You're right. The reason that's right is because, but this isn't measuring the right thing. The reason that's right is to go 1 unit in Y, you would need to go for 3 months, because you've gone about 1/3 of a unit in Y over 30 days. So that's correct.
Yes. Okay. Right.
Okay, but so what does that mean? So the question is, what is the go down to look at where you were fitting, where you were computing the differential equation, because that was there we go. What is, we're trying to compute Okay, what we're trying to get is the lifetime of that exponential distribution, where we claim that you can reproduce the data. So if you go scroll down a bit, because you've got PDF, you're plotting the log of
the most relevant one. So if we want this to be, so let's look at what this is. This is this crazy function. Let's just say, can I just do it like this? Yeah. Okay. So that's the function.
Okay.
And so we want the slope. Well, it's not very linear necessarily. Although I think its slope is probably about the same as this one.
Yeah, let's just use that one.
Let's just see. Yeah, the slope is the same as this one, let's say. So so then let's just look at this one. And if we put this in here, this is the function. We want the slope of, the slope of this one is 1 over, it's this. This is the slope. So if we just make this that other number, that
well, then the answer is
1 over 111.
Yeah, then that means the slope is, okay, what does that mean? That means that that is very bizarre.
Well, no, but that would mean that the mean, that's not right.
The average time to becoming symptomatic is 3 months.
Which is totally crazy.
That's wrong.
Totally
that's
crazy.
Wrong.
That's not going to do good things for the economy.
Which is totally... Yeah, but why? I don't understand how, if you start with a population at t equals 0 in this picture, and you're asking...
Well, wait, hold on. This was based on the idea of the relationship to this slope here was basically saying, okay, if we sort of simplistically assume that 100% of cases were infected beforehand, right, or were infected before the lockdown measures and stuff were taken in, what do you expect the curve to look like? But if you include some amount of transmission after lockdown, etc., then how does that change the curve?
Right. Well, what in fact this is saying is it doesn't make sense. It's not. This is not really consistent with pure, free flowing, with sort of pure free decay, right? Pure free decay to get this result would imply that the lifetime is 100 days, right? I think. Which
well, except
wrong.
you can't get down to 0, right? You can only get down to 1.
Sure. So what? That's at some point you hit the limit of where the continuum approximation breaks down. Anyway, I think we should probably wrap this up. And if people have found this interesting, let us know, and we could continue this at a different time. I thought there was. Maybe we should. We might try and package this notebook and make it available to people, and maybe some folks on this live stream or elsewhere can figure out some more to this analysis, and maybe we'll tweet some of the pictures that we've generated from this out. I think I'm really taken with that picture that shows linear the linear decrease in ratios, because I find that a very encouraging picture. Unless we made a mistake, which I don't think we did, because we checked it a bunch of different ways. That's a really interesting picture. Okay, now let's see. We have a bunch of live streams scheduled this week. I believe I'm signed up to do one tomorrow, very different from this one. I'm signed up to do a for kids and others, a general science Q&A, and I think its title is Anything About Science Q&A. So very different type of live stream, but I'm looking forward to it. And encourage kids who are bored to show up and ask difficult questions, and I'll do my best. Okay. Well, thanks for coming to this live stream, and let us know. And we will try and package up this notebook and send it out for people who are interested. You can try it out on the cloud or on your desktop versions of Wolfram language. And thanks for coming. And Christopher, thank you for being about at least twice as efficient as I would have been, in if not more so, in actually getting all of these things to work. Okay, see you all soon.
See ya.
Yep, thanks.